Everybody remember that process which I created for myself. So let me just rewind. So there are three types of nodes: active, inactive, and neutral. We're starting with one particular vertex V. At this point, everybody is neutral, and we're going to explore. So these are all my n minus n minus one other. Why does it look like that? Is this S0 is defined to be 1. What is S1? S0 plus. So I'm going to simply try to impact everybody who has an H with me. That will be, let's say, x1 and a -1, so that I make this guy inactive, and anybody who has an H becomes active. The number of active nodes is S1 at time 1, and this progresses. And I only touch from a, I will go at arbitrary time t, look at any one of the active nodes, and look at all the neutral nodes to which I have an H. So this is what my process looks. So Sn plus xn minus 1. But what is the distribution of xn? With what and what? It's not a symbol. It depends on xn. I should not use. So keep reminding me that I should not use. What are the new entries into the active set? Remember, I'm at time t. So t minus 1 are already been turned inactive. So remaining nodes are n minus t minus 1. And how much more? ST also I have ST minus 1 also I have to take out because they have been turned into inactive. So it should be n. Make sure that n minus t minus 1. ST minus 1. This is my process. So last time what did we show? We showed that this process is dominated by a Poisson branching process with the same n comma p parameter. Now I want to lower bound it. That this process is going to dominate another Poisson branching process with a different set of parameters. So clearly I can do n minus n comma p. So I will do something smaller. Okay. What do I have to say? So this is the left hand side is my actual process. Component of P. Then equal to P is greater than equal to n minus 3. So this is the on the right hand side is the Poisson branching process. It's on writing n minus k comma. This new parameter k is what I have to give a select. Earlier, I turned this around with a p n comma p. That was my upper bound. I'm doing a lower bound with a slightly smaller parameter. There. T is the earliest time that it is clear, right? What we're doing. So XT hat is essentially the same way defined. Just that XT now are independent IID with binomial n minus k comma p. That's all it's going. Those are the two distinct processes. So here it should be. Sorry. Is it not clear what I'm comparing? Not clear, ask me that. It will be meaningless to prove something without knowing what we're trying to say. No. This process is clear. For my actual Ardoshlani graph, what is the probability that the connected component of a particular vertex is greater than k? I want to show that this is greater than. Here it's only a binomial branching process with parameters n minus k comma p. I'm looking at the time by which the process stops. That's also the progeny distribution. All of this we have done multiple times. All right, so what should we do? Right, indicated something last time. So for proving the lower bound, we produced a coupling to say that if something is happening in this process, I can add something and produce the new binomial process. And so it better be that one dominates the other. If we do the reverse direction, now I can take this has to be the weaker one, this to be the larger one, and somehow produce that this value at each time. Essentially, the xt I have to produce as a function of xt hat, such that xt is always larger than xt hat. That's all I have to do. Everybody with me? That's what I did last time. I produced xt hat equal to xt plus something, which was non-negative. So I knew xt hat was always larger. Now I'm moving the reverse direction. So I have to produce xt as a function of xt hat plus something. Now what is that something? Xt in this process, that must be known. So whatever you write, make sure that xt comes out of this distribution. Xt hat also we know what it is. Now what is that additive term which will make sure that it respects the distribution?
The binomial dynamic difference a minus
Go on. So what do I want? I want xt equal to xt hat plus something. So that they respect the right distribution. But xt hat is anyway I'm using that. But whatever I add, I have to make sure that xt ends up having the same distribution as here. That's all I mentioned. What is that?
binomial
So let's call it 1. Okay, so the same IT should be binomial.
t minus 1 plus ht minus 1 minus k.
So please,
T minus 1 plus ht minus 1 minus k.
okay. Is everybody with me? What is xt hat distribution?
Minus minus k component.
N minus, so
So,
yeah, sure. Okay, so what will happen? If you essentially adding up plus just that last time. Because the second parameter is n. So if you're going to add essentially disjoint, you can think of it as disjoint binomial distribution, you add it together, you end up getting the right distribution. Okay, but now how do I do this? I have to eventually claim this. So suppose this is your correct coupling. What do we know? That because this quantity is always greater than 0, xt is always stronger than xt at that much we know. How do I complete the proof here? Well, this is true. We also have to be slightly, because you're taking negative, right? You have to be slightly careful about what these indices are. 0, if it hits 0 or below, is meaningless. So you have to take slight care in defining, and that will actually be helpful in proving that. But is the idea clear? What we're trying to do? Essentially producing a coupling between xt and xt hat. And this is much weaker than before. This parameter k is actually going to trouble us. This is not an absolute coupling. For each k sitting here, you have to introduce a parameterized branching process with n minus k trials. So it's a bad thing. Earlier, I was able to just do n comma p. It had no dependence on what this k was. This is much weaker. But we should really appreciate that there is no hope of getting rid of this k here and still getting a lower bound. Because this process is shrinking very fast. But this process is going to continue. So you have to do something like this. One could try to do n by k also. That might be much weaker though. So appreciate what is going on before we actually end up doing this. In the upper bound, we also be sure that this was less than equal to n comma p. There was no k here. But parameter wise, the process did not have to worry about. So when I'm running the process, I don't have to look at what k I'm evaluating this problem. But for this, I have. So you ask me this question, I have to run a different branching process. Yes. Here I don't have. But there is no hope of this ever being sitting there. You can't really ask it, okay, can I do one by k? That's not what I'm with a sine flavor. Because this is much faster. So this is one way of doing it. This is not the only way of doing it. That's not trying to say that there could be, you could possibly do a stronger one. But there is one possible way which is sufficient. That's all. Okay, so let's just get it. So, the idea is exactly the same. I'm going to write a few more details just to make sure that everything is rigorous. So let's say n of r is the number of neutral nodes. Actually, highest step has been taken. Let k be a stopping time minimum of time t such that n t is less than equal to n minus. The number of neutral nodes is shrinking. So eventually it will cross this threshold of n minus k. It will go below that. The earliest time at which it does, that's my definition of tau. So this will make sure that whatever I'm defining it remains non-zero. Because I'll only define from time 0 to tau. Or I think after tau. So if C of V is greater than or equal to K, what can I say about tau? So the size of the connected component of V is greater than K. What can I say about Do they look like the same? What can you say about tau k? Upper bounded, lower bounded. Remember the process, right? How it's progressing. How many nodes change their status from neutral to active at each step? Yeah. So that's what I mean. Nodes are neutral to begin with. At each step, some of them turn into active. So number of neutral nodes is coming down. So this tau k is definitely finite, and it will happen that at some point t it will go below n minus k. So if the size of the connected component is greater than k, how large can tau k be?
K.
Can you do better? K is true, but you can do slightly
K
better.
minus.
Okay. Why not k minus 2? The question clear? So what is the most trivial bound you can give me?
When each step one node becomes neutral to active.
Very good.
So in K steps you have less than equal to n minus k neutral.
Okay. Why is it so difficult? Is the question clear? Are you able to visualize what is going on? NT is decreasing. N1 was n minus 1. N2 is as many nodes I have turned from neutral to active. Subtract that out from whatever was initially there. So what is NT? Or rather, let's say NI. Will you say something about NI? What is NI? At most? Just bound NI. That will be helpful. So initially it was n minus 1. And at each step, how much is being subtracted? At least 1. So what's the easiest bound you can give me in there? I've done I steps. What's the maximum value of n? N minus I. Why? Minus 1 plus 1. Figure it out. So number of nodes at time 1 is n minus 1. The starting state itself is n minus 1. And in each step, at least 1 goes out. Otherwise, I will stop. So how much should it be?
N minus 1.
Not minus 1.
So N1 is n minus 1, N2 is n minus 2.
Okay.
So N is n minus 1.
Okay. So how much do I have? So 2 per minute. So at time I mean after I have done that time one. So that's why. So it's one more extra. I'm extracting one more out. So you should think of it as one step accelerated. So this is okay. This is actually less than count. Now can you tell me the bound on tau? So if connected component of V has a size greater than K, essentially my process is not stopped. That's all it means. Until time T. Until time K. So how large tau K can be? So this is going down, right? Is at most so much. So what is the earliest time by which I will go below a level n minus K? That's all I'm asking. So give me an upper bound on tau. Is the definition flipping around? What am I asking? Asking for the earliest time by which it goes below n minus k. I know in ith step it's so much. So by what step it is below n minus k? Just plant k here. That's all. So if I put k plus 1, what will happen here?
N minus k there.
That's all I wanted. So tau k is at most
minus
minus 1 plus 1. Not clear. It's not clear. Let's stop and do it again. Is this inequality okay?
Yeah.
Okay. Now I'm just putting what is the earliest time by which it goes below n minus k. So all I have to evaluate it is like when does this upper bound become at most n minus k. So by how many steps I can do that? And it's k minus. That's all I did. So now why is it useful to do this? Why am I worried about all this? Because there is a negative in what you're going to add. So I have to make sure that negative doesn't turn everything 0 or smaller than 0. That's all I'm worried about. So I essentially look at time going from 0 to tau k so that this quantity is at least n minus k. So that I can do the difference without having to worry about it. So this is nothing but an n sitting here. Do it everything from this. Okay. So as usual, xi is our Gardner graph. Xi hat is the binomial process. I'm going to add find another xi hat plus yi square. I distributed minus it's exactly the same as what you wrote. Now if I add these two, what happens? Xi hat has a distribution which is simply binomial of n minus k comma p. Don't know this. What is the distribution of xi? Binomial. What comma p in terms of ni? Simply ni minus. How much do I get to add? I exactly get to add the number of neutral nodes. Okay, that is one. Big problem. I don't know why we are going back and forth between them. What is this? This is exactly the number of neutral nodes at that point of time. I'm just writing with my now, if you put these three things together, you can see that xi has the right distribution. Because I'm creating this essentially new. You should not think of it, this is exactly that. I'm given xi hats. I'm adding a new random variable to produce this random variable. I just need to check that that has the same distribution as my actual understanding process. And that is true. We've seen last time also. And in the process, I also shown that xi because yi is unbiased. If you get stuck, ask me. I can't figure out if something is missing. That's it. I'm okay spending more time on anything. It's not good. So what's the good? Complete the proof now. Now there is nothing left. Now we have everything on the board. I just want you to write one punchline. It's all.
You want to show that dominance. Right?
Exactly, that's all I care. You just show me the dominance. That's
That is non-negative. So
why is non-negative? So this is obvious.
Hmm.
You can use this if you want. This is also useful. This implies this. So the probability of this event has some bearing on the probability of this event. That's right. So this is my understanding. And same process. We will change. Is everybody with me? That these two events are equal. This is tau. So all you have to show is one implies this and other implies that. What does this mean? Let's put it this way. That ST is greater than 0 for all t less than or equal to tau k. So definitely the process is still going on. So this implies that. That we already hit it. So both are equal. Now I can just control this. To control that, I can just control this. What is my ST? ST is ST minus 1 plus ST minus 1. And ST hat is ST hat minus 1 plus XT hat minus 1. And I already controlled XT and XT hat. What can I say? So if this is true with the hat, then this is also true because XT is bigger than XT hat. Yes. So what is the relationship between this quantity and ST hat?
ST is greater than ST hat.
See, XT hat is smaller than XT. That's what we should.
Yes.
XI is dominated by XI. So which direction will I go here now? Let me write it now. Which inequality goes? Which is larger. So if this is true, then that is also true. So this way. And what is this inequality? This is exactly my t greater than k. By the same logic, is also equal to and what? Writing so many things without doing anything. bunch line was right here. But I can write xi as a summation of two non-negative quantities, where one of them is xi hat, other is something I created for myself, and made sure that xi is the same distribution as that. That's all I have. Now, once you have this, essentially you should just see it from here, that this process is stronger than this process. So if this process is dying out, this will die out only later. That's all it's going. All that is rehashing the writing. So the number of progeny I'm creating with xi hat is smaller than the number of progeny I'm creating with xi. So the time at which the process dies out, it better be that hat process dies out before without hat. That's the order. I still feel there is something not working out. Some hesitation or something. It's all okay. Okay. So with that, let's go to the punchline really. How large? Connected. So I gave you some discussion to work out last time. Anybody again? It's a hand maybe way of thinking about what cannot happen, like how large can the connected component be, given that P of n is something. Can you try that? Right now. Okay, so let's define. I don't like this noise. U to be the frequency. Of vertices. Do not. By giant I mean order n. Make sense? So what should you converge to if n is large? What is it is frequency? So frequency, frequency of vertices. So total number of vertices divided. So total number of vertices that are not part of giant fraction. So total number of vertices which are not part of giant component divided by the total number of vertices. That's what U is. So where should you converge if n is large? See, all of this is angry. So take it with a pinch of salt, but it's very enlightening. It gets you worried on, even though it's not the most rigorous thing to do. This is definition clear, right? So let me just make a picture. Suppose this is my color. So all these nodes are part of the giant. Okay. And there are several other nodes which are lying. So inside, outside doesn't matter because topology is not important here. And these are all nodes that are not part of the giant component. So the frequency of is nothing but number of these guys divided by the number of guys inside. There is no inside outside, so don't get confused by the geometry. All these red nodes are representing is that part of a giant component. And these guys could be connected, but they're not part of the giant component. So now think of where should you converge to as n goes large. What would be the right interpretation of U?
So U is total nodes outside divided by the total number of nodes in the term by n.
So fraction of nodes that are not part of the giant.
Yes. It should be 0. Right? So as I add it depends on the value of P, right?
So don't worry, I'm not asking you to compute it. All I'm asking is, as n goes large, what is the right interpretation for you? What is U?
If I'm above the threshold, then
No, don't worry about it. You're not trying to compute the value of it. All I'm asking is how should I interpret U? So think about the following. You take a big bag, certain number of balls are red, certain number of balls are blue. Or okay, that's not a good idea. But that number is fixed. Yeah, let's take binomial with n comma p. What should be the corresponding thing here?
Yeah. So the extra node that I'll add.
No, don't add subtract anything. N is given to you. For any n, u is the fraction. Now, as n goes to infinity, where do you think fraction should go?
If there is a giant component, then you will be decreasing.
No, I'm not asking increasing, decreasing. I'm just asking for interpretation. I'm not trying to do anything on upper bound, lower bound. English is what I want. In English, what does it mean? As n goes to infinity, what does u mean to us?
It will be a distribution.
Not a distribution. It's just a fraction. It possibly has a distribution. What is the value fraction go to? Is there some probability of something?
Probability of existence of a giant.
No. It's a probability that a node belongs to the giant. That's why. Isn't it?
It's not clear. I mean, it's the opposite, right? Probability of not belonging.
Okay, so sorry, we take the
Yeah.
probability of a node not belonging to you. That's okay. Is that okay? Use a fraction of nodes. If there is any sensibility in this frequency is like weak law of large numbers, if you think about it.
This is probability of absence of the giant.
No, anything. If I were to look at what am I trying to do? This is nothing but the expected value. The random variable better go close to the expected value because of weak law of large. So as n goes to infinity, it will converge to its mean. Where mean is nothing but the probability of a particular node or a uniformly picked up node to not belong to the giant component. Oh, so let's play with that. So let's take U to be the probability that is not part of that. Now comes the interesting question of how should you write U as a function of U, P, and N. That's what a recursion would look like. U as a function of U, but it will also involve P's and N's. So now think about, is there anything which you can think about?
So, for thinking about this, we need to first work in the regime where the giant component exists, right?
That's the whole point. I'm trying to find out is U.
If giant component doesn't exist, then you is like one.
Think of the opposite. If U goes to 1, what happens to the giant component? Exactly. So that's what we're after. So we're after the fact that depending on U, something is going to happen to the giant component. So when does U go to 1? That's really what we're after. So anything which comes to mind. So think of this node. Let's say this is my one particular node, which has arrived late. Everybody else is on time to the party, and the graph is formed, giant component. Now, what can you talk? Suppose I was looking at this nodes as the node under consideration. What can you say? Is it okay?
Yeah.
But here you assume that they will.
See, no, I'm not assuming anything. All I'm saying is the same thing. Now, what is the probability that this guy becomes part or not, doesn't become part of the giant component? And with n nodes and n plus 1 nodes, you wouldn't expect anything to change. That's what I'm saying. So keep this one node out. Let everybody else form the graph, do whatever you want. And now just consider this particular graph. Now for this guy to become part of the giant component or not become part of the giant component, what has to happen?
Should not have an edge with anything about it.
Oh, so let's take one by one. Okay, so let's call this X and let's call this Y. We'll worry about all Y's one at a time. Now between X and Y, what has to happen? Either there is no edge, so there is no question. And what is that probability? It's 1 minus B, independent of everything else. That is this 1 minus B. Now suppose there is an edge. Then what is the event that this does not become part of the giant component? That this guy is not part of the giant component. So that is P times G. Remember, n and n plus 1 should not have any difference. So I'm playing this game with n nodes, then I'm just suddenly adding one more. N is large enough, you assume that nothing is going to change. This is correct? Now, how many such y's exist?
You tax.
No, how many y's exist? N minus 1. See, I am late to the party. Everybody
We
else
have
is
to
late.
consider
There are
the.
minus 1 of them.
Yeah.
So this to happen, essentially for each of them, this has to, that I don't become part of it. So I can simply write this to the power n minus 1. So this is slightly handy. But so these are not really independent events. This guy is not part of giant component. This guy also is not part of giant component. There are some correlations. But let's just at a high level, this is what is one can think of. Is this a reasonable relationship you can think of? What really happened? I came in. The fact that I don't get to join this giant component, either I don't have an edge to a y, or I have an edge, but the y is itself not connected. And this has to be true for every possible node, because otherwise I'll become part of the giant component. So that's why taking the complement is easier. So now you're good to go. So what is the solution for you? This is not rigorous, it gives the right answer. That's amazing. So it's not too bad to think about this. That's the whole part. Even though we have taken some liberties, the answers are not very different. Is it clear what happened? Now can somebody tell me? So the regime of interest is something times 1 by n. That's our regime of interest. So think about if P of n is smaller than 1 by n, what are possible solutions to you?
What is one solution?
Okay. But is that the only solution that you
No, that is not.
So you have to somehow argue that if P of n is less than 1 by n, that's the only solution. To get what you want. And u equal to 1 implies that there is no giant. That's the big picture. It's a very simple recursion, but it's pretty revealing. You know, how do I get that if this is true? The only solution is u equal. I missed a different way of making a mistake. What do partially recorded?
Wait, I got a notification from YouTube that.
Yes. At least do the reverse thing.
Today's plan, right? Yeah, it's there.
Yeah. I think it's- So I don't have to hit two buttons. One button is enough. I missed. Okay. Okay. All right. So at least to physicists, this should appeal more. Deepak Dhar would do this. You read any of his papers? He suddenly latches onto some interesting lessons like this, and bam, out comes an answer. If you read any of his 1981 papers, this is how it is done. Beautiful. And all of them are rigorous. Especially the sandpile model.
Yeah.
So this is a lesson that are very useful and beautiful as well. Now, how do I proceed? It's not too difficult. Just if you look at such an equation, what would you do? Do that first thing.
Plot.
You won't do that. Why differentiate? Yes, something is in the exponent. What do you do to handle the exponent?
Yeah. Okay. The second.
Okay. What next? Sorry.
And
Find the law. Very ugly. You don't want to do anything ugly. That will be super ugly. I don't even remember that 1 minus x. Or what is the series of law? No one knows this. Something much clearer. All you can use is the log inequality. What happens to log of 1 plus x or 1 minus x when x is small? That you can use.
what's
Log of 1 minus x when x is small. That's some nice approximation.
less than less.
X itself.
Like, yeah.
Essentially, that you can do. That would be argument. Sorry, that's opening it up and throwing away all the lower order.
Yeah.
Okay, I accept. Accept it. Okay, so suppose I do that. What do I get? You can do this by inspection. Essentially.
The log.
You can also replace p by I lambda by n. If you want. Eventually put lambda as that. All of this is small, u is less than 1. So this quantity is definitely 1 minus something positive. So all of this is small, I can actually throw away the log. So what do I get? Log u is equal to n minus 1 times something. What is that something? 1 minus p. U minus 1. P times u minus 1.
Yeah.
So what is the final answer? This will be in terms of u.
What did I say in the n minus 1? I mean, you're throwing out the bigger term then.
No, just look at the log and approximate it. You'll get a p common, right?
Yeah,
That
yeah.
is lambda by n.
Yeah.
So n's will disappear. That's the important thing. Otherwise, I'll be stuck with an n. So again, n minus 1 will be same as n.
Lambda equal to 1.
Answer is lambda equal to 1. I want an,
Lambda is one to put, right?
I want an equation in terms of u and lambda. That's it.
And not n.
N will disappear because n minus 1 by n.
Okay, okay. So this log u is basically lambda multiplied by.
Yeah, so this is is equal to minus lambda or lambda n.
Lambda u minus 1. I mean,
So just tell me log u is equal to how much?
u lambda u minus lambda multiplied by.
Minus lambda minus
Yeah.
So what does this equation look like? Very familiar equation. Now you can take away the log. Mu is equal to e to the minus lambda. This is not a bad equation. Okay. No, never seen such equation. What is this? U is equal to, it's very similar to what we did for computing the what probability?
Eta.
But that's not very difficult. Then now you can easily show that if lambda is 1, there is no other solution. So if lambda is less than 1, there is no way they can actually meet. Except at u equal to 1. That's the punchline. So you get a hand wavy result, and as long as
For arbitrary PN,
not arbitrary PN. I'm showing you exactly for any lambda less than 1.
why would we put P to be lambda?
Why? It's sufficient to prove this, right?
Yeah, because you can take, I mean,
I can take whatever value. Anyway, it's monotonicity approved.
Yeah.
So as long as lambda is less than 1, the probability is going to 1. That is, there is no giant count. On the flip side, I'll also show that as long as greater than 1, there is a giant count. So you complete the picture. So there is no room to move. This is only half the picture. The picture is very simple. That's why. I didn't need anything. All I did was just somehow manufacture a recurrence relationship. And which happens to be exactly typed. So this also tells you that this approximation is not bad. It's like there are few approximations to be made here, but they're not bad. It is giving you the full picture. So it's very important to get both the intuition as well as the rigorous answer. So now I'll do the rigorous answer. That as long as lambda is less than 1, the probability that a giant component of size bigger than log n exists, that is quite large.
Giant component of size log is
Less than. So essentially we'll show that
Yeah.
the giant component is of size log n, nothing more.
log.
With high probability, your giant components are of size log n. You can't get, so by definition, giant component is order n, so there is no giant.
Okay.
So the largest size of the connected component is of order log n.
Log.
Okay. This you have seen before. Definition of I lambda. Essentially coming from the Chevron form. Lambda. This you have seen before. Definition of I lambda. Essentially coming from this rate function. I call it the rate function. Okay, so there. Right. Lambda less than 1. Right. Lambda was nothing but then for every a greater than 1 bar I lambda defined upon the exists and delta. It's then essentially a function of the comma lambda greater than 0. Like that. Connected. Now let's call it max. Greater than equal to 80 log. So C max is take connected components of all vertices, take the max over all possible vertices. Fine? That's what C max is. And cardinality is just the number of nodes in that. What is it saying? That the probability that I can find the largest connected component to be of size greater than 8 times log n is decreasing at n to the minus delta, where delta is greater than 0. So essentially, this result is with high probability, the largest connected component is of size less than a log n. That's what I'm saying.
Delta is like a
Delta is
power exponent.
yeah, there exists one. That's all. It will depend on both A and lambda. Okay, so who will prove this? I sketched out the idea last time. We have lower upper bounded this process, the process we want to control by a binomial branching process. But for a one particular vertex.
Yes.
But here I want C max.
Yes.
So what is the simplest way I can control this?
So you just,
Supreme. Supreme over what?
overall the values.
Yes, but there are n of them. So what's the simplest bound you can do? Union bound. So n times. So if I fix a particular vertex, then I can control the probability of its component size to be larger than 8 times log n. The connected component, this cannot be n. The probability of this cannot be more than n times the probability of.
No, I didn't get it.
So you fix one particular vertex.
Hmm.
We already know that the connected component size of one particular vertex is dominated by the binomial branching process, for which I can possibly compute the probability that T for that process is greater than 8 times log n, because it's nothing but a simple process for which we have seen the distribution. Now, the fact is I'm not looking for one particular vertex, but I'm looking for C max. So essentially max over all possible vertices, because there are at most n of them. So if I do one, the probability of this happening is at most n times the probability of that one particular connected component to be larger. So whatever number I get is, as long as it is smaller than n to the power 1 minus delta, I should be okay. Sorry, minus 1 minus delta. That's all I want. Okay, finish the. That's all there is to do. You might have to recall your Chernobyl bound. Because you want to control the probability that capital T is greater than T for the binomial process. But the idea is very simple. If you get stuck, if the idea is clear, then you should not be hesitating.
We are considering binomial.
You can consider whatever. We have shown something for one particular process.
Yes.
So if you want to use some other binomial process, you don't have to show it for that process. We have shown a dominance only for one particular process, which was n comma p binomial. So that is ready-made available. If you want to do something else, you'll have to do more work. That's all. So first fix a node, use the dominance, and then spread that one particular node to every other node in that. That's all. This is clear from the domination for one particular vertex.
Yeah.
But what is this process doesn't worry about the process. This is just the total progeny size or the time at which this process dies out. So if this is greater than t, ST hat is definitely greater than 0 because that's the earliest time at which it goes to 0. By definition, ST hat is nothing but this minus t. So it better be that all these sums, the sum of this is greater than or equal to t. What is the definition of ST hat? It is exactly x1 hat plus x2 hat to xt hat minus t. But these are now IID sequences. Now we can forget about what it is. You can just use the Chernoff bound directly here. This is at most. Anybody doesn't know that. E to the minus. So that is where the rate function enters into the picture. The lambda is the same, n times p lambda for both the processes. So this we did many classes about. Sum of IID random variables to be greater than t is bounded by e to the minus t times I lambda.
What is I lambda?
Just a function of lambda.
Okay.
And lambda is nothing but n times p. So this is application of German. It's called something. It's not German. But we did this, so it's German. Oh, so we're done?
The right hand side will be n minus k. Right?
No. First dominance is less than equal to. That was independent of k. This is a process which is growing much faster. We did two dominants.
Okay.
One was we dominated the Ardashirani graph by a binomial random process with n comma p.
Previous.
Yes, that's what. Because I want to dominate. See, I'm showing
This is
a bad result in some sense, where the component size, the largest component size is at most order log n. So what I have to show is that in this process itself, it's at most log n. So there's no way you can have more than log n there. When I'm going to go the reverse direction, then I'll use n minus. At least so much is happening in the binomial process. So at least so much has to happen in the Ardashirani process also. Okay, so are we done? For one vertex, I've done this. For all possible n vertices. So what is this equation is 1. What is this connection to? C max greater than t square equal to n times the problem is that PV is greater than t. This is by brute force union 1. So how much do I get? I get n times p to the minus p times I lambda. Now if I plant t equal to how much? A log n. That's what I'm interested in. What do I get? Our evaluation for the t of interest is a times log n. That's what we want to show, that this probability is going to go to 0. So at t equal to a log n, what is the right hand side? It raised to 1 minus n times e to the minus a log n times I lambda. So now a and I lambda have to have some relationship. That is why the theorem said for a greater than 1 over I lambda. So for a greater than 1 over I lambda, the product is greater than 1. That is why this term is going to dominate there. That's why I needed a to be greater than 1 over. But that is a fixed constant. So lambda is a fixed number. Therefore, as long as a is greater than 1 over lambda, the quantity is only the minus delta. What is the delta? Write down exactly what delta is. is nothing but 1 minus a times I lambda. Precisely that. But what depends on both a and lambda. This proof is easy once you have the domination. Without the domination, you don't get this. So this is the usual method. So this is a very simple process, even for very complicated processes. This is the usual direction one takes. You somehow find a branching process for which we know something, or put it below, show that it's dominated by something, and show it from the top. It dominates something and sandwich this process in between. And hope that the sandwiching is right. Not always it's right. In this case, it will be right. Not every time. Just a happy accident next time. Any question on this? What is going on?
It is delta here, so A is greater than 1 by I lambda.
Yeah.
So
So that's
that is
beside.
something positive, the brackets.
Yeah, that's what I want, right? Delta has to be greater than 0. Otherwise, it is going somewhere meaningless. So the exponent has to be positive.
You're saying it's a happy accident that it's tight. How do we know it's tight?
That will show next class. So what we have shown so far is that as long as a greater than 1 by I lambda, the largest size of the connected component is growing as a log. Now essentially we'll flip it around and say suddenly it goes to n. That's what. That's how the thresholds are shown. So one you really think of 1 by n. Be slightly below 1 by n, all components are of size log n at most. Just above 1 over n, there is definitely at least one component which is of order n, that's unique. That's also one has to show. But the uniqueness is not that difficult. Suppose there are 2 of them. What is the probability that there is no edge connecting between them? And that will be very small. So that's what we really mean by the unique. With high probability, it's possible that 2 giant components do exist. It's just the probability of that happening is because that you can understand. That n nodes here and n nodes here have no connection between each other. That is the three there. How many pairs exist? There is too many pairs. N square pairs is it. Okay, so now let's look at some. So this is not put it in homework, but an exercise you should definitely do. Not an obvious thing. So let me use my definition. Yeah. This process. So yeah, I need definition. Define a nice. So what is the distribution of n of I? As a function of n of I minus 1. That's an interesting topic. Distribution of n as a function of n I minus 1.
And I mean, so minus x.
So xt is already here. Xt we know. So can you write n of I in terms of n of I minus 1 x xi? I want you to write n of I as a function of n of I minus 1 and xi. So I can go back to this if you want. You can just think of it. How many neutral nodes get reduced in one time? XT. So the difference has to be XT. If I give you that, what inference can you draw about the distribution of n of I as a function of n of I minus 1? Because xi is distributed distance. What is this quantity? N minus t minus 1 minus st.
This was the number of neutral nodes.
Ni is Ni minus 1 minus binomial with Ni minus 1.
Right. So what is the distribution? There is some strange property of binomial distribution. That I will write. When I didn't know that was true. So the interesting property.
And then Ni is 1 minus 2.
Then X is weird. So first statement is given to you. M is a fixed number. So y is m minus x and is binomial distributed m comma 1 minus p. Then x is nothing but binomial m comma. This you can prove. This is basically that. Fun exercise. This was what it implies is that given that my n p is n p minus 1 minus xt. N p minus this fun exercise will imply this. We'll use this to prove an alternate proof of the previous theorem. Is this property? And what this will imply is ST plus P minus. So what is happening is that this is, so T is showing up as an exponent of this, while the first component remains n minus 1. Initially, the way we saw ST was a complicated process. ST was ST minus 1 plus XT, where XT itself is in the first coordinate, it depended on ST minus 1. What we are able to do is to shift, keep this constant, and shift all the dependence on T over here. So this is exercise number 1. It's not really an exercise. Once you see this is obvious. But you just use that. So what is n of 1? It is n minus 1. Or n of 0 then minus 1. So you just keep doing recursion. You'll get that answer and you'll get this. So really the fun exercise is this. Once you show this. Okay, so suppose you are given this. The final result. Can you show the previous theorem without having to go to the dominance? Now you don't need to use dominance. That's the good part of it. So you are given this, that ST plus T minus 1 is binomially distributed with n minus 1 and this parameter. Now all you have to show is that the process dies out, or the connected component of the process doesn't have size larger than A times. There's no dominance needed. So can somebody sketch what will we do? Now ST is directly connected to the connected component. What is the relationship? That if the connected component is larger than T, then S of T is greater than 0. That's it like that. All you have to compute is what is the probability that S of T is greater than 0 for one particular vertex, and plant an n from the outside. What is the probability that ST is greater than 0? This binomial is greater than T. That's all. And that you can compute. Pretty straightforward. So all the work is in this fun exercise. Once you have this is automatic. I'll write this item down, the probability the C or B greater than T. It's same as probability. Rest of T greater than 0. And so T is greater than 0. That's correct. And this is because this is binomially distributed. All you need to do is to just turn it around. This can be computed. We have precise estimates for how large this is. Binomial distribution, you know, all you need to do is to take some exponent. So essentially proof without. So I also did not know this. So internalize this, like why is it even true? It's a weird, like what you're doing is, I'm not seeing anything like this. P goes to 1 minus P. That is what is weird about this. What you said earlier is you take two different binomials over n and k. You can put it n plus k. Here is something weird going on. The probabilities are getting conjugated. So that's really the big thing. Once you have this is straightforward. Clear, right? That once I have the distribution of this process, this will allow me to directly compute. I don't have to go via the dominance. And once I do it for any one particular vertex, I can do the union bound and go n times. So you get precise the same answer. And there's also no difference between the answers. So for every lambda, so every A less than or equal to 1 over I lambda, largest connected component size is not. All right, so that's all I have for today.